Hi everyone, welcome to Matt's Spellbook. I'm your host Peter, and basically we are going to continue on our, Proof Summer series with Sascha. So I will be getting on with Sascha pretty soon, so let me just get into my Discord here so he can join us. Alright. Hey Sascha, the stream has started. The floor's all yours.
Hey!
So the floor's all yours, my friend. Mm-hmm.
Is my mic fine?
Oh yeah, I can hear you loud and clear.
Okay, because I installed my AC today and I have like a lot of noise in my background.
Oh, okay. Yeah, you sound pretty loud and clear.
Okay. I guess Discord's noise cancelling is doing some magic here.
Oh, okay. All right, in chat, if you can't hear Sascha, let me know, and we'll probably work out the kinks with that.
It's kind of fantastic because like the AC is like, I don't know, like 2 or 3 feet away.
Oh, okay. I see.
It's pretty loud, so it's kind of, I hear it definitely, so it's kind of.
I don't hear it. Like, yeah, I just hear your voice.
That's awesome. Okay.
Mm-hmm.
So I guess for today we can maybe talk a little bit about the integers that we were building last time.
Yep.
And maybe after that we can maybe do a little bit of exercise.
Okay.
Because we did a lot of yapping, but we need to practice also.
Yeah, that's what I was thinking too, actually.
Yeah, so we'll just do a little bit of it, and after that we can go to exercise.
Okay. Did you get the link I sent you for the Excel board, Excel draw? Yeah.
Yeah.
Cool.
I just draw a line. I don't know if you see it.
Let me see. Okay, I see you.
Okay, yeah. I just jump on you. Okay, so recall.
Let me just erase some things here, because I think there's something blocking there. Okay. Sorry.
So recall. So last time we introduced the integers, and we said it was like, well, it was 2 copies of the natural number times some equivalence relationship. And the point was that so we were looking at couples x1, y1, where x and y are both natural numbers, and we were saying they're equivalent. Well, basically what we wanted is to treat this pair as if it was x1 minus y1, right?
And this has something in relation with the equivalence relation, right?
Yeah.
Okay.
So, I mean, the idea is to... Oh, okay, let me move a little bit. So the idea is we should think of those pair, x1, xy, let's say, as x minus y.
Okay.
And the relationship we chose to enforce that was to say, well, we're gonna say those two pair are equivalent if we have x1 plus y2 is equal to x2 plus y1.
Okay.
Okay. That was kind of a sneaky way to tell that if those two have the same difference, right?
Yeah.
But I mean, we cannot talk about negative numbers, so we had to work to find a workaround.
Yeah.
So I mean, just basically moving the term around allows us to do that.
Okay.
So maybe just to be sure, I will just cheat a little bit and just rewrite this equality here. We could write it as this, right? But here we might get into trouble because we don't know what this quantity means for a natural number. So so that's the motivation behind this equivalence relation.
Okay.
Okay. So I mean, there's a number of things we know an integer should have. So we should be able to recover the natural number inside of the integers.
Yeah.
We should have a notion of addition, multiplication. We should be able to tell if a number is negative, and so on, right?
Yeah.
So maybe let's look at one first properties. So the first property we'd like to have is somehow the natural number should be include inside of z, right?
Yeah.
And here I'm gonna put some
quotation marks.
Some quotation mark because obviously they're not the natural number is not a subset of z. Literally, right? With our definition. But what we would try to do is to find a subset of z, which basically is a natural number.
Okay.
Okay.
All right.
And the way we're gonna do it is we're gonna build a map from the natural number into the integers.
Okay.
Okay. And this map will have to respect a number of properties. First of all, we want it to be injective. So maybe I will call it phi.
Okay.
And we want a map to z. So basically, I mean, we have to go back maybe in the picture on the top we have. So if I would like to represent a natural number using this language, I probably want it to be something that looks like that. Like maybe I will write on the top. I want to map n to the pair n0, right? Because that would correspond to the positive integer n. If we look at what we want. So we're gonna take our map to be exactly that. So we take n and we map it to the so we cannot map it on the pair because we're on the quotient. So instead what we're doing is we put it in the equivalence class of this pair.
Okay.
Okay. And now we have to now we have to make sure that this map is reasonable. So for example, this map shouldn't squish natural numbers, right?
Right.
So for example, if I have what I would expect is if I have this equality for two natural number, in other words, I have m0 is equal to m0, I would like n to be equal to m.
Okay.
Because I don't want I mean, I don't want, for example, 1 to be equal to 2, right? I don't want I want to keep my natural number distinct, right?
Mm-hmm.
So this condition is basically checking if phi is injective.
Okay.
So first question is phi injective? So we're gonna run with just the definition of injective and see if that's the case.
Okay.
So to check if something is injective, you assume that you have, I mean, basically what I wrote on top. You assume that you have two elements whose image are equal. Okay.
Okay.
And from now you have to, I mean, write what this phi does. So here we said that phi is very simple. You just put a number into its equivalence class.
Okay.
Are we good so far?
Yeah. So basically, like, since we can't use, like, I'm just summarizing. So basically, since we don't have anything like, you know, the subtraction symbol or negative numbers, we're basically trying to use the equivalence relation to basically allow us to get too close to creating, I guess, like, the integers, the way they behave, right? So
yeah.
So are we like using the equivalence relation as to, I guess, reflect the behavior of negative numbers before we even know what negative numbers are?
Yeah.
Okay.
I mean, what you have to think here is we're kind of implementing the integers, right?
Uh-huh.
I mean, we all know what the integers are and how they should behave, but
yeah.
I mean, we don't have really a definition of them. Now here we're kind of trying to give a definition to them, which is
not a rigorous one, at least.
Yeah.
Okay.
So here we go. So okay, so the fact that those two the fact that those two equivalence class are equal,
yeah,
just mean that the pair n0 and m0 are equivalent.
Mm-hmm.
So what it's mean for those two pairs to be equivalent, if we unwrap the definition, it means, yeah?
No, I'm kind of remembering, so I'm just going to relay it back, like, just in case. So, like, you can correct me if I'm wrong in certain parts. So,
yeah,
if we have the equivalence class of, like, say, like, n of 0, right? So that means it must contain, like, the sets n, the set containing n, as well as the set containing n and 0, right?
Yeah, so I mean, that was a definition for a pair, right?
Yeah.
Yeah. But that was kind of, I mean, we introduced it yesterday just to have a definition and to say, well, that's not like some ill-defined concept. We can actually give it a definition, but now we will kind of forget about it. We just know that ordered pair exists and we can, I mean, they have the property we want, like, for example, the order matter and stuff like that. So.
No, I'm just trying to remember the definition so that way, like, it's just solidified in my head. That's why I asked if I was wrong or right about that.
Yeah, but you were right.
Okay.
So what was the equivalence relation on those two guys? So we said that those are equal if the first component of the first pair plus the second component of the second pair, here's 0, is equal to the first component of the second pair plus the second component of the first pair. So we can have a cross sum going on.
Oh, okay.
So what we end up is we end up with this equality, right?
Right.
Because the second term of both things are zeros. Well, I mean, if we assume that we prove all the property of natural number, but when we add by 0, it just do nothing.
Mm-hmm.
So we are left with n equal m. Yeah. But does what we show? As we've shown, that if we have the image of phi are equals, this implies that n is equal to m. In other words, phi is injective.
right, so like to reflect on what you just wrote, right? So to prove that it is injective, we basically just use the equivalence relation between the two pairs, right?
Yeah.
So when you pick, so basically when you have n and 0 and m and 0, like, did you just pick 0 to make it more convenient, or was that like actually a logical step for you to actually like implement in this proof? Or you just picked it because it was convenient?
I mean, I just didn't want to change it, right? Because the map we describe on the top just says, well, take n, make a couple where n is the first component, 0 is the other component, and just look at the equivalence class of that couple, right?
And phi here, is it supposed to represent like, say, a function?
Yeah, that's a function.
Okay.
That's a function from n to z, and the definition is given on top here.
Okay. Right.
And what we've shown is that this phi is injective.
Okay.
Okay. Usually when people write injective map, they sometimes had a little bit of notation on it. Okay? They usually write something like that. Like they write an arrow, but they made it a little bit curly on the left hand.
Interesting.
So this is usually mean that this map is injective.
Oh, okay.
And they also have a similar notation for surjective. Maybe I can just write it on the left. So usually when they want to have a function which is surjective, they maybe sometimes put a double.
An arrow with double arrowhead.
Yeah.
Okay.
But anyways, so the reason why they use injective, they put an arrow with the curl like that.
Yeah.
It's because it's supposed to remind you the inclusion symbol.
Oh, okay.
So when you have an injective map from a set to another set, you can pretty much treat this guy as if it was a subset of Z.
Oh, okay.
In the sense that Z contains a subset which is in bijection with the integers. With the natural number, sorry.
So basically, like, if we're thinking like functions, like what we learned in like high school, it's more like the input is sort of treated as I guess a subset. If it is injective, it basically is treated as like a subset onto the output set, right?
Yeah. Yeah.
Okay.
We don't always want to think like that, but usually it's useful. Sometimes it's useful. Here it's a case which it makes sense.
So it's loose. So it's a loose definition then. So basically, it's like it's not completely wrong, but it's like something to keep in mind in case you want to be clever or something like that.
Yeah.
Okay.
Yeah. So this allows us to define, if you want, that allows us to define a new definition for the natural number, at least as a subset of Z. Now the natural number will be defined as the set of equivalence class of the following forms.
Okay.
So that's a new way. Or another way of saying it is that, well, I mean, here the notation will be a bit confusing, but n is the image of n.
Okay.
And here you have to understand with this definition. I'll put the prime just to clarify that those two are, I mean, formally are different, but in practice we will usually treat them the two definitions as the same.
Okay.
Okay. Some subset of that which are in bijection with the natural number, right?
Right.
And sometimes people will say the natural number embed into the integers. like the way you think is there is a copy of the natural number inside of the integers.
Okay.
And we're gonna see that again and again. So for example, when we're gonna go to the rational number, well, we know that the rational number have a copy of the integers, right?
Mm-hmm.
So we would have to show, well, there is a subset of the rational, which is the integers.
Yeah. But before we continue on, Sascha, welcome raiders. Thank you, Zach, for the raid. Much appreciated. So we got a lot more coming into the lecture halls, Sascha. So we're basically talking about, basically he's showing us how to create the integers. So, like, if you want to create some mathematical magic with us, sit down, relax, just chill with us. All right, Sascha, the floor is back to you.
All right. So we're gonna try to define some arithmetic properties. So I mean, obviously the integer must have addition, otherwise it would be very weird, right?
Yeah.
So let's define addition. So addition will be, well, you know, addition is a binary operation, right? It takes two things and give you another number, right?
Mm-hmm.
So it's gonna be a function defined on z cross z, which give you another integers.
Mm-hmm.
Okay. And here we're gonna write a prototype for a definition, but it will not be obvious that this definition makes sense. Okay. I will explain why.
Mm-hmm.
So maybe I can write it in the other form. So let's say I want to add up x1. I want to add up this integer with this integers. Right.
Right.
What would be like the obvious thing to do? Like, if you had like to guess a definition for addition.
I mean, since it's a pair, I usually just pair the like terms together. Like add each like term together.
So you mean like do it component wise, right?
Yeah, like x plus x1 plus x2 and y1 plus y2.
Yeah. So we could define it as something like that, right?
Yeah, that's what I would
say.
say.
But here I have a little bit of a warning to tell you. Which is something you always have to keep in mind, is that you see here we're using like integers, right?
Right.
And here we so those guys are sets, right? Of pairs.
Yeah.
And what we did is we basically look at this set and chose one, right? And we pretty much did the same thing for the second thing, right?
Right.
And we said with the very one we chose, do this addition, right? The question is, okay, maybe there is other, pair we could have choose which are in the same equivalence class, right?
Right.
So does this definition depends on that?
Okay.
In other words, if I don't know, if x1 y1 is equivalent to what can I use? Let's say maybe x3.
Okay.
y3. And we have like a similar thing for x2 y2, which is equivalent to another pair. Let's say x4 y4. The question is, does x1 plus x2 y1 plus y2 is equivalent to x3 plus x4 y3 y4? That's something we have to answer.
Okay.
So do you see like what is possibly the problem here?
Let's see. Well, the thing is that we don't know what, like, you know, x1, x2, or like any of these numbers are, so for them to be equivalent, would they have to be like elements of the integer set, or would they have to be the same element in this case?
Yeah. They're the same element. So okay, maybe I can just write it as a concrete example. So let's say, so we know for example that 4-2 is equivalent to 2-0, right? I mean, we can just easily check that's the case. So the question is, for example, if I have another pair, let's say 3-0, and we have here 5-2. Do we get the same thing if I do first? Well, so my question is 4-2 plus 3-0 is equivalent to 0 plus 5-2?
No. Oh wait. Oh yeah, they would be.
Yeah, and you have to convince yourself that I mean, if they weren't, the definition we write on top is rubbish.
This one?
Yeah, it will be rubbish, right? Because in the quotient set, 4-2 and 2-0 are exactly the same thing. The quotient doesn't see the difference between the two. They're exactly the same thing.
Okay.
So if we do addition like point-wise, and for example we change our representation,
yeah,
and we don't get the same answer, we did something wrong. This is not well defined on the quotient.
Okay.
So we have to check that.
Okay.
Yep.
All right.
So, I mean, this basically just gonna end up doing a lot of arithmetic computation. So
okay,
let's do it.
Okay.
On the exercise I assigned for this week, the fifth exercise will be something similar.
Okay.
Where you have to make sure that it makes sense to actually add up modular numbers.
Okay.
It doesn't depend on the choice of representation you choose.
Okay.
Okay. Okay, let's do it. So what is given is that x1, y1 is equivalent to x3, y3, and x2, y4 is equivalent to
before we continue, Sascha,
yeah.
One of the chat, let's see, adds3 says, what is the, I think it's supposed to be the equivalence relation on that example. I guess they're asking.
So it's the same from above. If we scroll back all the way to the top.
Which part do you want me to show them?
Like the first part we did, like when I wrote recall and I say those two pair are equivalent if we have the following.
It's all right. Like, thank you for joining us, actually. And if you guys like math and physics, or just need like a stream to keep you productive, you know, drop a follow. Much appreciated. That way we can learn together. Okay,
okay.
Sascha. Yep. Here we are.
So we're gonna do the proof. So are you ready?
Yeah.
So we have to check that those two things are equivalent. So if we use the definition, it say, well, look at the first part of this guy and the second part of this guy. Add them together and check if you get the same thing as if you were adding those two guys together, right? That's a equivalence relation.
Okay.
So let's write both sides.
All right.
We have x1 plus x2 plus y3 plus y4. Okay.
Okay.
So that's maybe we can call it our left side, where I'm going to use the color green for that.
Okay.
and the right side is what is
Blue.
it? It's x3 plus x4 plus y1 plus y2. And the question is, are those two equal?
Okay.
And what we know is that we have, our hypothesis is we have those two pairs which are equivalents, right? So, here we obviously need to use this hypothesis, otherwise it's probably not true. So we're just gonna rewrite what those hypotheses mean.
Okay.
So the fact that x1, y1 is equivalent to x3, y3, right? This just tell us that x1 plus y3 is equal to x3 plus y1, right?
Right.
And we can do exactly the same thing. We can just unravel the definition for the second pairs. For y4. And we'll get something very similar. Oops. I got distracted.
No, it's okay.
x4 plus y2.
Okay.
And now we need to use this bloody mess to verify this equality here.
Okay.
The one we want to check.
Okay.
So one thing which is probably natural to do is maybe to add up those two equalities, right? So if we add up those together, we're gonna get x1 plus y3 plus x2 plus y4, right? And if we look at okay, so this is the left side. So let me maybe just rewrite the right side also. So if I add up those two guys together, we get x3 plus y1 plus x4 plus y2. Okay.
Okay.
Okay. Now we kind of get a mess, right? Now we have a lot of terms.
Yeah.
Now it's a good time to remind us what we want to do.
Okay.
So what we want to do is we want to prove this equality, right?
Yeah.
So let's see how this equality we want to prove compare with the one we just got under it.
Okay.
Can you see something similar between the two?
Let's see here. So we have the first one in green. Let's see. So the first term on the bottom, right? X1 plus, is that Y3 or Y4?
Yeah, that's a Y3.
Okay.
Y3, yeah.
Okay, I just want to make sure. Okay, that looks like it's right. And then this one. It looks as if, like, from what I can see, it looks like it's about right. Yeah, like the right side and the left side are reflective. It's just that the terms are like in different places.
Yeah,
But
so
then
you agree
again,
with me that...
But then again, it's addition, so like the way it's arranged doesn't matter.
Exactly. So you agree with me that the left part on the equality we get at the bottom.
Yeah.
What color I use? I use green. I use blue. Okay.
Yeah.
It correspond to the green part and the
blue
the
part.
guy on the correspond to the blue part. I mean, up to commutative of addition, right? We can just rearrange the term and we're done, right?
Yeah.
Obviously, this is equal to 1x plus 2 plus what is it? Y3 y4 x3 plus x4.
So what is the rule that basically, like, you said that basically it's the first term plus the second term, right?
Yeah.
Where does that rule come from again?
So you mean the reason why I was able to take those two equality and add them up?
Yeah, like why is it that you do the second term? That's the one thing I'm trying to remember. Like what
Wait,
was the
Adam, I'm not sure to follow.
So you basically said like when we did x1 plus x2, basically you said something about like we had to I think we had to basically add the second term within the pair. I think that's what you said. Where does that rule specifically come from?
Oh, it comes. Okay, so you mean why we did check those two guys?
Yes.
Oh, because we want to check if. So our initial goal was to show that those two pairs are equivalent.
Okay.
And our equivalence relationship said that okay, basically look at those sum and check if this sum is equal.
Yeah, because like right, I remember like with the green one, you basically put x1 plus x2, and then it's plus like y3 plus y4.
Yeah.
So my question is that why is it that you have to add the first term on the first pair to the second term in the second pair? Like where's that? What is that rule like? Like why do we do that? That's my question.
Yeah. Okay. So we call it. We said that two pairs are equivalent.
Right.
So let's say A1 is equivalent to A2 B2.
Mm-hmm.
If we have A1 plus B2 is equal to A2 plus B1.
Oh, okay. Right? Now I see what you mean.
Yeah.
Okay.
And basically here you can just treat it as A1, B1, A2, B2, right?
Okay. Yeah. Now I see that. Okay. That makes sense. Because for it to be an equivalent relation, it has to be both. I forgot what the first one is, but it also has to be symmetric as well as transitive.
Yeah. The first one is reflective.
Reflective. Yeah. It has to be reflective, transitive, and symmetric. Okay.
Yeah.
That makes sense. All right. So this proves that. So we're done proving this is, what we were trying to do in this case.
So okay, let's go back to what was the main idea. So we wrote some definition for addition, right?
Yeah.
But here we had sort of a trouble, right? Because our definition just say okay, so we have those equivalence class, right?
Yeah.
And I mean, in the equivalence class, they can have a lot of things, right? For example, if we look at the equivalence class of 2,0, there is like a lot of things inside of it. There's like 2,0, obviously. There is like 4,2. There is 3,1.
Mm-hmm.
There is a lot of pair we could have chosen, right?
Yeah.
I mean, there's an infinite amount of pair we could have chosen.
As long as they are equivalent to each other.
Yeah. And what we did in our definition is we said, okay, pick one. For example, x1, y1, and pick another one in the second equivalence in the sequence class you want to add. And with those two guys that you chose, arbitrary.
Yeah.
You will add them.
Okay.
Point wise, right?
Right. Yeah.
But the problem was, what if I don't know, Peter? I picked 2,0 in the class, and for example, Peter, you took 4,2, right?
Yeah.
Are we gonna end up with the same answer? That's the question we were trying to answer.
Oh, okay.
So what we did here is we said, okay, let's check it if I don't know, maybe I took the pair x1 y1 and x2 y2, right?
Yeah.
I chose those to do the computation, and you, Peter, you decide to choose the other guys.
Okay.
I mean, at the end of the day, those two are equivalent. So when I do the computation on my side, and when you do the computation on your side, we should end up with the same answer.
Same result. Yeah.
Yeah. So what I did is I computed addition on my part, which is the left part.
Yeah.
And when you did the computation on your part, which is the right part, you get
side.
that.
Okay.
Yeah. And now the question is, do we have the same answers? And what we check is, indeed, we get the same thing.
Okay.
I mean, at least our answer are equivalent, so the quotient we are the same.
Yeah. Okay.
So you do see like the.
Yeah,
like,
I see the overall idea. At first, I thought like I was wrong in my logic, and you're trying to show me like there's something deeper to it. But then, like when I saw you do it, I was like, oh, okay. So we're just proving that my idea was right. It's just that I didn't have the intuition on the abstract level on why it's right.
Yeah.
Okay.
And it's pretty much you kind of see it's kind of painful, right, to do this kind of check.
Yeah, it is rigorous.
So, yeah, but we will have like to check it for many things, right?
So...
Whenever we work with quotient, we always have to make sure that our definition does not depend on the particular choice we made.
Yeah, it like it really doesn't matter as long as it reflects the same pattern.
Yeah.
Right. So ads 3 ask, I have a question. Does this property change if we are in the real numbers?
So, I mean, the real number will be another kind of beast, but the real number at the end of the day will be also some, they will be like some kind of quotient also. So the real number will be built from a similar thing. So we're going to have like some kind of set, which, I mean, I don't want to explain it right now because it's a bit complicated.
Yeah, and it'll probably come at like next lesson or like probably a few lessons down the road.
Yeah. And now what we have, we're going to have some equivalence relationship on that set. Okay.
Ads basically says, no, I mean just this property. Ads also says, I'm not building anything.
Okay. I mean, basically, all we did here is just to check that addition is well defined for integers. So, of course, for the real number, we're gonna have some notion of addition. So, yeah.
All right. What's next?
Okay. So, there's kind of the problem here was that we have to make sure that whatever representative we chose, our definition doesn't matter, right? That was kind of the point.
Yeah.
What it would be nice is if we're able in every equivalence class to be able to find a unique representation that satisfies some kind of properties.
Okay.
Okay. So I mean that's not mandatory, but we start to want to do it.
Okay.
Okay. Maybe I just want to give an example of something which is not well defined here.
Okay.
To kind of see you where can the danger goes.
Okay.
So let's say I can define the following function. Maybe I can call it P because it's pretty much projection.
Okay.
Which takes Z and give you a natural number. Okay.
Okay.
And what it does is it takes, I mean, oops, that's not what I meant to do. So, I mean, we can define it as formula. We can say, okay, well, look at some integer, which is the equivalence class of pairs.
Yeah.
Take a representative and just throw the first component.
Okay.
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 And the question is this well defined?
Is this well defined? Is that what you're asking?
Yeah.
Okay.
Yeah. So in the sense, if AB is equivalent to A prime B prime, do we still get the same answers?
Okay. We're still doing like addition in this case?
No, here I'm just doing something a little bit simpler. I'm just projecting the first component.
Just the equivalence. Okay.
So basically, what I'm taking is I have a pair of natural number, and I'm just like throwing out I'm just keeping the first component.
Okay.
And I want to see if this is well defined on Z.
Okay. So prime, and then b plus a prime.
So here you have to be a little bit careful because at the end you get a, right?
Yeah.
So what I should get is that p of ab should be equals to that, right?
Mm-hmm.
Because in the eyes of the integers, I mean, those two guys are the same, right?
Right.
The pair AB and the pair AB prime are the same because of the equivalence relation. And the question is those two map equals. The answer is no. And we can actually do it with like a concrete example. So let's take two. Okay. So let's say I chose the pair 2 0.
Okay.
And what pair do you want to take, which is equivalent to 2 0?
Let's go with 4 2.
Yeah, 4 2. Let's say you chose 4 2.
Mm-hmm.
So if we look at the definition of a function, what it says, okay, pick your representation and throw the first component, right? Mm-hmm. So if I do the computation with 2 0, I would say, well, the projection of 2 0 would be just 2, right?
Yeah.
And if you do it on your side, what you're gonna say is the answer should be 4, right?
Let's see. Because I'm trying to remember the definition of the equivalence. Because then it'll be 4, this set of 4, then 4 2. So yeah, I think it would be 4.
It would be 4. But here we're kind of in a trouble, right?
Yeah. Because,
I mean, at the end of the day, the class 2 0 and the class 4 2 are the same, right?
Yeah.
So what is up with this function? Well, this is not a function, right? Because we give it exactly the same input and it gives us different results. So P is not well defined. I don't know if you get my point or not.
Let me just go back a little bit. So basically you're saying because it's not well defined, we basically don't know exactly what to do with A and B. For even in our numeral example, you're basically saying that we have the numbers and by their equivalence relation, they are the same, but but we haven't defined exactly what they're doing to each other. That's why we have different values, because we haven't defined exactly what exactly P is doing on them.
Yeah, I mean, we kind of use a loose definition, right?
Yeah.
We said, well, I mean, if maybe we're lucky, this definition will not depend on the specific choice of pair of AB, right? But that's not the case here.
Okay.
In this definition, it does matter, right? Because I mean, if we go to the concrete example, I chose 2 0 and used 4 2, and we didn't get the same answer.
Right.
So we might be able, to write some compelling formula for such a function, but this function wouldn't make sense on Z. So that's the reason why we have to be careful when we are talking about equivalence relationship and quotient sets.
Okay.
And usually when you work with quotient, you always have to ask, I mean, that's very a habit you have to take you have to build is whenever you do something in the quotient, you always have to answer why it's well defined. If I change my if I pick something else in the equivalence class, does the definition still make sense? Okay. So what we would like to do now is to be able to avoid this, avoid the problem of having to choose a representative in the class. We would like to have like some kind of canonical choice.
Okay. And what's a canonical choice?
So we would like to look at some pairs which only occur once in each equivalence class. So let me give you an example, right?
Mm-hmm.
So let's take the equivalence class 4-2, right? And as we said before, there's many pairs we can choose, right?
Mm-hmm.
We can choose obviously 4-2 itself. We can use 4-2-0. We can use 3-1. We can use 5-3. I mean, we can use 5 bazillion plus 2 5 bazillion. That would also work. I mean, there's like an infinite amount of pair, right?
So when we're making the equivalence relation, right?
Right.
I understand like when we have 4-2-2-0, right?
Yeah.
Because I notice in the other two, like when I add like say this first term and the second term, it equals like I think like for 5-3 it would equal to 8, like or like if you minus it will equal 2. So I'm just wondering how you're getting the pairs, just to remind myself.
Oh, so I'm getting the pairs. So yeah.
Yeah.
So basically our equivalence relationship are just looking at the difference of the two components.
Oh, okay. The difference of the two components.
So here you see it's 2, here you see it's 2, here you see it's also 2. So that's all I'm able to make up.
Oh, okay. I think it's because I know we haven't formally defined subtraction. That's why I was.
Yeah. I mean, if you go back to the very top.
Yeah.
I wrote, the definition of our equivalence class. But I also talk about, we only have addition right now, so we cannot really talk about subtraction.
Subtraction, yeah.
But if we had subtraction, this equivalence class would just be that thing. The equivalence relation will just be the thing on screen.
Oh, okay.
So you're basically just comparing the difference between the components. That's our equivalence class.
Okay, so the pairs are basically representing the two numbers, but the equivalence class, the equivalence class is basically saying there's a relationship between these two. It's just that it's not, I guess, obviously defined yet. Right?
I mean, we had defined it, right?
Yeah. I'm just saying, like, abstractly, if you're basically writing just relationships.
Yeah. Okay, so we'd like to be able to choose a canonical choice.
Mm-hmm.
And, if we use a little bit of our intuition about how integers should behave, we know there should be only two kinds of integers, right?
Right.
I mean, roughly speaking, there should be only the natural integers and minus the natural integers, right?
Yeah, the negative ones.
So what we're gonna try to do is show that any pairs, any equivalence class, we call it AB.
Okay.
Admit a unique element of one of the following forms. So it's going to be either the first component is, either the second component is 0 or the first component. Oh, sorry, I wrote the same thing twice. Maybe I should just see. All right.
Okay.
Do you do you want to see like a concrete example?
Sure. So basically, I'm just gonna reread what you wrote. So the equivalence relation of AB emits a unique element of one of the following forms. Okay.
So if, for example, if we take, I don't know, 7-1,
Yeah.
what would be our, I mean, I would call those a canonical choice, okay?
Uh-huh.
Or canonical representation. Can you tell me what would be the canonical representation of this class?
So, like, what's it equivalent to? Like, what sets it will produce?
Like, okay, so for example, you see in 4-2, if we look at the example above,
Yeah.
we're able to find an element, namely here 2-0, which has the form I want.
Okay.
Here I'm asking, can you find a similar element in this equivalence class which has the property I want?
Okay, so I would have to say probably like 6-0 or 0-6.
No, 6-0, right?
Yeah.
So I agree. 7-1 and 6-0 are equivalent, so 6-0 will be our canonical representation of that class. Okay, but 0-6 will not be, right?
Right.
Because 7-1 and 0-6 are.
It says or. I forgot that there was an or there.
Okay. What about if I swap the order?
If you swap the order, then I would have to say 0-6 at that point.
Exactly.
Okay.
So I mean, now we check. We've checked that we can do it. Now the question is, can we do it in general? Like, does it always exist for any classes?
Okay.
I mean, you sort of figure out the recipes, right?
Sorta, yeah, because like if the higher digit is on the second one, then basically it would be equated to like 0C, or in this case, so if it's like, if A is less than B, then basically C will be in the second part of the pair. Whilst if A is greater than B, then basically C will be on the first term of the pair.
Exactly, yeah. Okay, so let's do it. So first so here I claim two things, okay? I use the word admits, which is missing an S, but whatever.
Yeah.
And also I use the word unique.
Okay.
So admit is basically just a synonym for existence. And unique is, unique.
yeah, it's like it's one of its kind.
Yeah. So we're gonna first show that this always exists, and after that we're gonna show it's unique.
Okay.
So assume we have a pair A1, B1. Okay. I don't want to have more indices, so let's just call it A.
And B, okay.
Yeah. And when you were doing your analysis, you just told me, you were kind of reflecting on the fact that A is greater than B or B is greater than A will be something that matters, right? So it's probably a good idea to break the
logic.
The problem in two cases, right? So case one. Okay, let's do the cooler one. A is greater than B, and case 2 will be the A smaller than B. And that's a B, that's not a 6, okay?
Okay. No, it's fine. It's fine. I kind of assumed it was going to be B.
Okay. So let's do case 1. So for case 1, we know that A is bigger than B, right?
Yeah.
So what does it mean for A to be bigger than B?
Like, what does it mean?
Yeah.
Well, technically, it would probably be equated to like A would have to equal B plus some some natural number.
Exactly. You see, you're good. We gave the definition yesterday. You told me that you haven't seen the definition before, and now you're able to.
No, I was just breaking it down because it's like if the number is supposed to be higher than something, what does that mean? And I'm thinking like abstractly. I'm like, oh, that means it has to be that number plus something else.
Yeah. Yeah. I mean, you see the definition I gave yesterday was kind of natural.
Mm-hmm. Yeah.
So what it means, it's A is equal to B plus C.
Mm-hmm.
And so now that we have this equality, so what do you think the canonical choice would be if you look at this equality?
The canonical choice?
The canonical choice, like the pair that looks like something like, oh, well, I don't want to give it the answer right away, but it has zeroed somewhere in the pairs.
Oh, okay. I think I just got confused because I'm like trying to equate what you're asking without you having to give the answer. That's why I repeated it. So because I'm trying to think of how to write the proof, but at the same time it's like maybe I'm thinking too much, and that's what's causing me to like not come up with the answer right away.
Yeah, okay.
But I'm breaking down the logic in my head, so like if I get stuff wrong, you can just like tell me where I'm going off. So there exists a C with the element, which is basically an element of the natural numbers. A is equal to B plus C. So in other words, now I'm trying not to basically do what the algebra student usually does, which is like subtract C from A, subtract C from A. I'm trying not to do that. That's why I'm starting to like struggle a little bit. But let's see, implies that there exists a C, which means I would have to say that I'm not gonna say like let's see, like B subtracted by A equals C, but I'm going to say basically there's a relationship that basically says like AR and ARB is equivalent to C, like some relationship there.
Okay, so maybe when we're kind of stuck like that in the proof, it's usually a good idea to restate what we're trying to prove.
The definition?
Yeah, so let's maybe restate what we want. So what we want?
Yeah.
So what we're given is we had a pair, AB, and we want to find some other pairs, which is given by E0 or maybe a 0E. And now the goal is to find such a E. Okay. That's like our goal, right?
Yeah.
So here maybe you have to use a little bit of your instinct or intuition. What do you think will be our E in that case?
I would have to say I would have to say in this case it would have to be C, the pair C0.
Exactly. So we're gonna write that. So we're gonna say, does A is equivalent to C0?
Okay. Yeah, and then we have to prove that part.
Yeah. So if we want to prove that, we're just gonna unravel the definition. So what does it mean for this pair to be equivalence? It means that again, A plus 0 is equal to B plus C. Right?
Right.
Of course, we can remove the plus 0, so we're just left with B plus C. right?
Okay, right.
But that's exactly what we had.
What we started with. Okay.
Right. So maybe we can call this maybe 1.
Uh-huh.
So that's exactly 1.
Okay. So then, so we would be done with case 1, right?
Yeah. So does AB is equivalent to C0?
Okay, so for like case 2 then. So that.
If I want, I can let you do case 2 on your own.
Yeah, that's what I was
I
thinking
think-
about doing.
Yeah, because I think you're getting very good.
So in this case, then there exists C, which is an element of the natural numbers. A. Whoop. There we go. A is equal to. No, because then it would be B is equal to A plus C. So then the equivalence class in that case would have to be okay. Then at that point, I think that's what we're aiming for. Is that?
Yeah. Give me just a second because my SkyDrive is kind of bugged right now.
Oh, okay. No problem.
We just reload the scene.
Mhm.
Yeah. There was like a few part that was missing when I was.
Oh, like basically like some parts are missing. Okay.
Yeah. Is this thing happy now? Oh, okay. I see part of it. Maybe I gave it a second to load. Yeah, I'm having a hard time to.
Like how I got it yesterday
No.
with what you wrote.
Yeah, so maybe I would just upping on Twitch and see what you have. Oh, I got a nut.
Yeah, it's like
We would
about.
have to wait 20 seconds. Yeah. Yeah. Just
Yeah.
one thing I was a bit sloppy when I wrote my proof is I forgot to put the equivalence arrow at every step,
Oh, okay.
which I should have done. But I think you got it right. So basically, I was able to see like 3/4 of your proof is just like some part were missing, and I wanted to see the whole thing. So I F5 my page, but
Uh-huh.
I guess I shouldn't have done that.
It's
Okay, let's
fine.
see. So usually what I like, you basically get the idea. You basically nail the idea. Okay.
Okay.
So maybe I can just give you some tips about the writing.
Yeah, because I feel like maybe the structure is not right in some way.
Yeah. Even though if in my prop writing on the top I was not very clean also.
Mm-hmm.
So usually what you would like is, usually when I write a proof like that, I would write. You see on your third line, which is like the equivalence class of AB is equal to the equivalence class of 0C.
Yeah.
I would put on the left the word claim.
Which one? The third line?
Yeah.
So like claim like right here?
Yeah.
Okay.
Just to stress the fact that I want to show that now.
Okay.
Like it's I don't know yet if it's true, but I want to show it's a thing.
Adds 3 basically says only missing the tilde with the equivalence class relation. Oh, so like I'm guessing where it's the line where it says claim, like the equivalence class of AB is equal to the equivalence class of 0C. Should that be a tilde, Sascha?
No, because in that case they're literally equal. They literally is the same set.
Oh, okay.
But basically, when you write that the two equivalence class are equal, it's the same thing as writing that AB is equivalent to 0C with the tilde, like the way you wrote.
So the only thing I was missing in the proof was just basically claim that the equivalence relations are the same. Oh, okay.
Yeah, and after that I would probably put the if and only if for every step.
Oh, like where would I put like if and only if?
Just after the claim. So you will have, I want to show those two classes are equivalent, right?
Uh-huh.
But this proposition is equivalent to the fact that we have the equality on the line after, right?
Uh-huh.
And after that, the line that follows from that is just basically you just say adding 0 doesn't do anything, right? Mm-hmm. But that's a if and only if.
So basically it should be claimed if and only if, like, you know, the equivalence relation of these two pairs and equals the equivalence relation of these two pairs, right?
Yeah, we'll try to reload the thing, so maybe I can guide you a little bit more, because...
Yeah, if not, then we can make a new one.
Yeah, I think we have to make a new one.
Yeah, we can make a new one. Yeah, because the weird thing is that whenever I just go onto Excel Draw, it just reloads the last one I did. It doesn't make a completely new thing. But I'm a physicist, not a pure maths person now. Oh, that's cool. Actually, I need to learn physics too, Ad. So if you want to join our Discord server, you're more than happy to do so. That way we can talk physics together. If you're up for that. Because I actually need to learn physics a little bit more, because like I've been delving deep into math a lot. I feel like I have to balance it out. So are you sending a new
I guess
Excel draw?
I can. I guess I can.
Yeah,
I never remember.
I don't know why it basically uploads the last. I mean, it brings up the last Excel draw I did. I guess I have to like try to refresh it every time we start one.
Yeah. Okay, here's the link.
Okay, open it. I'll close this old one. Okay, I think I'm...
All right. So okay, so what we did? Okay, maybe I will just write the proof very quickly. So
yeah, nice and empty.
Oops, I over zoom it. So what we did is case 2. Mm-hmm. Case 2 was assuming that A is smaller than B. We can find a canonical representation, right?
Okay.
So what we did is okay. So the fact that A is lower than B, mm-hmm. So A is lower than B, implies there exists a C in the natural number, such that we have A plus C is equal to B, right?
Right.
And after that, we used a little bit of our intuition, and we said, well, I think the representation will be the pair 0C, the canonical representation.
Yeah.
So what we do is I claim, maybe I can write like that, I claim that AB is equal to 0C. And to go with the comment someone put in the chat, the statement that those two equivalence class are the same is exactly the same thing as saying that AB is equivalent to 0C. Okay.
Okay.
That's the same thing. And now we can prove the claim. So proof of the claim. Maybe if I want to feel fancy, I can say proof of the claim. So what we have here is that AB is equivalent to 0C is equivalent. So I would put the double arrow sign like that.
Yeah.
To the fact, so I will just restate the definition. So it's equivalent to the fact that AC is equal to B.
B plus 0. Yeah.
Yeah. And maybe if I want to feel extra, I mean, sometimes it's nice when you start, when you do proof to put the reason why. Yeah, I would say that's by definition of the equivalence relation.
Okay.
By definition of a relationship.
Okay.
And after that, I can say, well, this thing is equivalent to A plus C equal B. And this could be 0 is the additive identity. Could be the reason why. Okay.
Okay.
And now, if I go back to the thing, so maybe I would like to name something. So maybe I will say, okay, this equality I had here, which I deduced from the fact that A is smaller than B. Let's call it 1. Well, if I look here, this logical statement that A plus C is equal to B, this is true. This is exactly one.
Wait, what is exactly 1?
Okay, so that's what I mean. Okay, so if you go back on the top, you will see that I wrote A plus C is equal to B, right?
Yeah.
And I put a little 1 here, just to give it a name, okay?
Okay.
And I say, well, so using the fact that A is smaller than B, we deduce this equality, right? So we know it's true.
Oh, okay. Like you're reading a book and you're basically referencing the equation. Okay. I thought it was something involving with the proof. I was like, okay.
Yeah. So I'm like, okay, this equality holds because that's exactly equality 1 that we know it's true, right? So as our proof only use if and only if, double arrow like that. That means that A plus C is equal to B is equivalent to the thing we wanted to prove on the top. Thus, AB is equivalent to 0C. I mean, that's basically what you wrote. I just like...
okay. Just wrote it.
Yeah.
Okay.
Okay, but you did a fantastic job.
Oh, thank you.
Okay, so this so we're not completely done, right?
Right.
So we've shown so far that any equivalence class AB has a canonical representation.
And a canonical representation has to be unique and what else?
I mean, we just know it exists and it's unique, right?
Okay.
But now we've just shown existence, right? Now we have to
prove its uniqueness.
Yeah, and here if you look at my wording choice, I use the word a, right?
Yeah.
A canonical representation. I don't say the canonical representation. That's what we want now.
Mm-hmm.
So let's show the uniqueness part. So what we want is, let's say we have two canonical representation.
Mm-hmm.
Of, let's say, AB. Okay, and let's call our canonical representation, maybe we can call it C0 and C prime. Okay. I mean, it's kind of annoying because we have to do like 3 cases, but I mean, two cases will be similar, and one we will just show it's not possible to happen unless 0. But okay. Okay, so let me just call those canonical representation. I don't want to force it there. This one, let's just say it's P1 and P2. Okay.
Okay.
But P1 and P2 are just pairs. Okay.
Okay.
We want to show P1 is equal to P2.
Okay.
Yeah. So here we're gonna have a couple cases. We basically have 3 cases. So case 1 is the case where P1 is equal to C0 and P2 is equal to C prime 0. Okay?
Okay.
So they both like in the same form in where the second component is 0. Okay?
Okay.
The second case is very similar, and we'll see the proof is kind of just it's basically just the same proof as the first case.
Mm-hmm.
Is the case where C1 is given by 0C and P2 is given by 0C prime.
Okay.
And the case 3 will be when we have a cluster. Like one of them is this form, and the other guys is given by that.
Okay.
Okay. I mean, obviously, we will see that case 3 can only happen in a very specific case. I mean, what's your intuition telling you on case 3?
So if we have an equivalence with those two, then basically it'll just be having C equals C prime, and if they're 2 different numbers, then it wouldn't make sense. We would have a contradiction at that point.
Yeah. I mean, in most cases, but there's one case that this can be possible is if C is equal to 0.
Mm-hmm.
Then we're out of the. We're okay.
Yeah, because I'm guessing C prime is supposed to be a different type of number. It's not supposed to be equal to C.
Yeah, usually not. So proof of case 1. Okay.
Mm-hmm.
So I'm gonna do it. So we know they're both canonical representation of the same elements, right?
Mm-hmm.
So I mean, so here I'm just gonna. I mean, here I don't even have to do the case. It would be true for all the cases. But the fact that P1 is equivalent to AB,
mm-hmm.
and the fact that P2 is equivalent to AB.
Mm-hmm.
Well, we've seen yesterday that equivalence class have transitivity, right?
Yeah.
So this would imply that P1 is equivalent to P2.
Yeah.
So we're gonna use this fact a lot. So let's do case 1. So here I'm just stating in general because I don't need to do the case analysis. This will be always true.
Mm-hmm.
So for case 1, so we have P1 which is given by C0 and P2 which is given by similar pairs. Okay.
Okay.
So what does it mean for P1 to be equivalent to P2? Well, this implies that C plus 0 is equal to C prime plus 0,
Plus
right?
0, yeah.
So what we get at the end is we just get, well, I guess we can cancel out the 0, so we're left with C is equal to
C prime.
Thus, P1 is equal to P2.
Okay.
And now you can probably get that case 2 will be exactly the same thing.
Yeah.
Just we're gonna get the opposite thing. So we're just gonna say case 2 is similar to case 1.
Normally in a proof you would have to do the same thing, or would you just state that in the proof?
Well, I mean, if you want to be 100% logically current, you would have to
write the whole thing,
right?
Oh,
Yeah,
okay.
but usually, I mean, people would just write, well, that's the same case. It's just like the coordinates are changed, so
yeah,
we don't have to worry about it. It's the same proof. I mean, I definitely do that a lot, and then I just did it. So I guess I'm
Okay.
guilty.
Even if you write a final copy of a proof?
Yeah.
Oh wow. I thought that you would have to write the whole thing just to be professional at it.
Well, sometimes that's kind of hard in proof writing. Is sometimes you can have like a perfect proof which is like logically flawless,
Yeah.
but it's very hard to read for others people because there are too much details and too much details can sometimes be very confusing.
Yeah.
So you sometimes have to strike between like a balance of having all the important detail in the proof and being readable for others.
So you could basically write what you wrote for case 2 and basically hopefully probably mathematicians will be like, oh, thank you for writing that, because I don't have to read that case.
Yeah.
It's like when mathematicians say, well, obviously this has to be this, and like when someone that doesn't know math proofs, they're like, wait, what do you mean obviously? I don't get it.
Yeah. I mean, here I'm not taking things too obvious, but sometimes like in books or in more advanced topic, you see, oh yeah, if I blow up that thing and I pull back along the
it's like they say stuff like, it's like obviously it is equal to this, and you're like, wait, how is that obvious? You didn't write the steps.
In one of the topics we use a lot in geometry is homological algebra, and homological algebra is known to have a commutative diagram.
Oh, okay.
Which is like basically you have function like that.
Yeah.
Like a square, maybe like that.
Yeah.
Maybe let's call it Fj and let's call it
L.
L.
Isn't that also in category theory as well? Like these type of
Yeah.
Oh my goodness.
Category theory, I mean, homological algebra is pretty much like some part of category theory.
Oh wow.
So you have like diagram like that, and they say they commute if you compose along those two morphisms, those two functions, you get the same thing as if you were commuting like that. And sometimes it feels like, well, obviously this diagram commutes. And then you look at the diagram, what the map doing is like, oh yeah, it's integrating against a fiber bundle and stuff like that. You're like, oh my god.
Oh my gosh, yeah.
I
remember you said you read a paper by Jim Simon, I think, like about fiber bundles.
Oh yeah, no, I was just mentioning that some of his work was about fiber.
Yeah. That I hope I can get up to that point of understanding what those are.
I mean, about commutative diagram, like usually it's a well-known fact that you have to be a little bit careful when there's sign involved.
Oh, okay.
Because I remember spending like a complete afternoon trying to work out the commutativity of some diagram that in the manual they were saying that in the textbook they were like stating, oh yeah, that's obvious that this diagram commutes. But whenever I check the commutativity of the diagram, I always get a sign, get like a minus sign, which is like the diagram differ by a minus sign. And it was like, what the hell? And then I realized that the proof had a sign mistake inside of it.
Oh no. The dreaded sign mistake.
Yeah, so I was not very happy about it. Okay, so so we have those two guys which are equivalents.
Yep. It's equivalent to that.
So this means that we have c plus c prime, is equal
to
zero. Yeah. But c and c primes are both natural numbers, right?
Yeah.
So the only way this is possible is that c is equal to c prime, which is equal to zero. Because c and c primes are inside the natural numbers. Thus, we still get the same conclusion. P1 is equal to P2.
Okay.
So we've shown existence and we show uniqueness. Which is pretty good now. And now I will show you something that we couldn't do before.
Okay.
Which was obviously when we're talking about integers like to high school students or even younger,
yeah,
they will say, well, there is like positive number. I mean, usually if you ask a layman what is an integer, he will just tell you, well, it's the natural number plus the negative part, right?
Yeah.
But so far we haven't been able to define what it's meant to be negative, right, or positive.
Right.
So with the canonical representation, now we're able to define it.
Okay.
So we say, so this thing is going to be a definition. So let's take an integers,
right,
which is just an equivalence class of pair ABs.
Yeah.
Yeah. So as we've seen before, we can pick the canonical. And here I want to stress I use the word "the," which in English usually means unique. Okay. And now we have first one. So maybe we can call the canonical representation class. Maybe we can call it C for canonical. I don't know.
Okay.
So we have two cases. We said that C is positive. We said that our integers is positive if the canonical choice is given by a pair like that. So the first component is, the second component is 0. And for negative, we do basically the same thing. It's just that we have C to be given by 0A instead. So now we were able to define the
negative numbers.
Positive and negative. Now we're able to we're able to understand what signs means.
Okay.
So here I want to stress the fact that previously this definition was not accessible for us. We were not able to write this definition because first of all, it was not obvious that every class contained an element of that, and furthermore, it was not obvious that this sort of writing was unique. But now we know it is.
Okay.
Okay.
Yep.
So from now on, we can represent every integers. We can write every integers as either the equivalence class of 0C or C0, right? But that's kind of heavy, right? First of all, we're writing pairs, and after that, we're putting like a square bracket to stress the fact that we're in a equivalence class and goes so on.
And plus the or also adds a little bit more.
Yeah.
Like you could use both, which is kind of like it kind of hurts your head a bit. This is when you think about it.
So instead of writing this now, what we're gonna write from now on is we're gonna write simply C for equivalence class whose canonical representation is given by C0, and we're gonna write minus C
for the equivalence class for 0C.
Yeah.
Okay. So now we're actually seeing the numbers form now. That's really cool. But I can see why they don't teach this in elementary school.
Yeah. You saw it was kind of formal.
Because I'm like, if proofwriting is so important for mathematicians and they really want to show the beauty of math, then why is it that they don't teach proofwriting for when you start learning math in school? And now I see why, because you have to know like a lot of like academic terms in this.
So we're gonna fix this notation from now on. I will no longer.
You will no longer use those. Okay.
Yeah.
You're just showing us to basically say, hey, mathematicians know how to prove that real negative numbers exist.
Yeah. Gosh. And it was kind of something once in our life we have to show that.
One question I have is that the proof for uniqueness.
Yeah.
I think like, so when you prove uniqueness, right? Is it the same type of method that we applied here, or will uniqueness differ depending upon which branch of math we're dealing with?
I mean, the gist of it is pretty much the same thing. So if you say yeah.
Okay.
So if you have like you want to show uniqueness, usually you want to assume that there exists like two things that verify your
idea,
your properties, and you want to show that those two things are equal.
Is it always usually in a case-by-case basis?
Not always.
Not always. So
I mean, usually it's not case by case. Here it's just because we have to deal with like some annoying cases where like the 0 can be on the left, it can be on the first
part.
Like
if x is equal to 0, or x is equal to some positive number, or x is equal to some negative number, right? Something like that, right? Like all those conditions. Okay.
Yeah, there's like I mean, that's kind of annoying to work with it, so we have to kind of do it case by case, but
the whole point of proving uniqueness is actually to prove that, I guess, like, the equivalence is going to be there, but you just change the variables within the properties of what you're doing, right? So, because in this instance, you have P1, which is equal to, like, C0, and P2, which is C prime 0. But the whole point of the uniqueness is to prove that these two things are equivalent, even though they have two different variables in it, right?
Yeah.
Okay.
So the point of uniqueness is now I can just refer to I can just basically forget that the integers are equivalence class of stuff. Now I can just think about the canonical representation.
Can you also use that same type of technique with functions? Like the same way to prove uniqueness within a function. Can you still can you do that with this type of proof technique?
So yeah, so I mean I'm not sure exactly which mean. So maybe sometime you will have like, I have there is one function that satisfies such properties. And what I will usually do is assume there is a second function that also verifies this property. Now I will show that those two functions are equal.
Okay, I see.
I mean, it's usually something like that. When you want to prove uniqueness, you usually assume there is another candidate, and you show that the second candidate is just the first one with another names.
Okay.
But usually, also something you have to be a little bit more careful when you read a little bit more advanced math.
Yeah.
Usually people will say they're unique, but usually they don't mean that it's unique. They usually mean unique to up to something.
Okay. Like unique to a certain point, right?
Yeah. For example, you might.
Go on.
So, for example, you might say, I don't know.
Because like one example I'm thinking of is the radius of convergence or the interval of convergence. Because I think that's kind of unique, but I don't know if uniqueness fits in that category.
Yeah, so unique in that case would be like truly unique, but sometimes, for example, I don't know, maybe in geometry, you have, for example, in Euclidean geometry, you can have a statement that you have a triangle with all the distance are 1.
Equilateral, yeah.
Yeah, and you might say this triangle is unique, right?
Yeah.
Like there is one triangle that verifies that.
Yeah.
But that's not actually the case, right?
Mm-hmm.
Because, for example, we can just, for example, flip the triangle. And if we're thinking of triangle as being points inside of the plane, right?
Yeah.
Yeah, obviously this set and this set are not the same. They're not the same points. They're not the they're not the same set of points in R2, right?
Yeah, they're just transformed differently.
Yeah, so we would say they're unique up to, for example, Euclidean transformation or translation and rotation.
Yeah. But it depends on which branch of math you're talking about, because like if it's like maybe if it's like group theory or something, like, you know, like if you turn that triangle a certain degree, it would be equivalent, but it's not equivalent in this case. But for someone who's like into geometry, it's like it's the same geometry, it's the same triangle, but it's just not in the same points.
Yeah, for example, you can I mean, sometimes you can show like there is like the integers are unique to some condition, and like you will be, well, I guess you can just give other names to integer.
Yeah.
So I mean, you don't really want to count them as separate, so you have to say unique up to
a certain
whatever
point.
you care. Yeah. For example, then triangle, but you don't really care about if the triangle is rotated or translated. Doesn't matter.
Okay. So what's next?
So shoot! I thought I only needed 1 hour to do the stuff, but I'm 1 hour and 43 minutes.
43 minutes. Yeah, you're on good time. You're on good time. So
I kind of took your time for your exercise, so maybe you want to.
Yeah, like what exercise do you had in mind?
So maybe we can have a look at the exercise in the PDF I sent you.
Okay. Let me just go in here on Discord. And if you guys want to follow along, if you have access to the Discord, it's basically under the channel assignments from stream. You can basically click on to the set theory and logic PDF. That's the lowest there. Oops. I don't want to. Actually, I think I have it on my file. Let me just open my file here.
So, I mean, maybe one of the things we can say today we did, which is probably not much if you tell to someone. Here we made sense in the integer what it's mean for what it's mean to be 4 in the integers. What it's mean. And we also made sense of what it means to be -4.
-4, yeah. I mean, that's still a good discovery.
Yeah.
Okay, here we go. Nope. I want to open it on my browser. Okay, here we go. All right. Hello, hello, Sensei. Welcome, Sensei Goon 69. What's the best part of your day so far? We just actually went through like proving. Well, Sascha basically taught us how to prove that the negative numbers exist in integers. So that's basically what's up. What's going on? So which one you want us to do? You want us to do what? Exercise 1?
Yeah, I mean whatever the ones you want to do right now, I guess.
Okay, so in exercise 1, you basically wrote, let f be a function from a to b, set a to set b, if x1 and x2 is a subset of A, and y1 and y2 is a subset of B, I'm guessing. We have the following. So I'm guessing with this first exercise, you want us to prove 1, 2, 3, 4, and 5, right?
Yeah.
Okay.
And in 2, I did a mistake. I put the 2 in the exposant.
I was like, that's peculiar, but I kind of thought that you were meant to put it in the subscript.
Yeah.
Yeah, that's fine. That's okay.
So I want you to do that, modulo the the typos in that question.
Okay, so I'm going to move this to my other screen so I can see it. But if you guys want to actually look at the assignment, it's under assignments on streams channel in the Discord, and it's the one that's the lowest one there. So it's the newest entry there. Just finished studying on a big math test that I have tomorrow. Oh, nice. What is the math test on, actually? I'm actually curious what subject it is. Okay, so I don't think we're gonna be able to finish everything, but we're gonna actually try to. So, exercise 1. Well, I'm not gonna rewrite everything because I think we already see what's on the question sheet. So.
Yeah, I pulled the sheet on my side.
Okay, so we'll write each question one at a time. So if x is a subset of x2, implies that x let's see, basically everything that we have done for the last 3 years. Oh, wow. That's a lot. Actually, Sensei, are you are you a high school student? Are you in university? What are you studying? Okay, so we gotta prove that x is a subset. If x is a subset, so proof. Are sets, and x1 is a subset of x2. And no, actually.
Here I will just add a little comment. So x1 x2 are both subset of A, and F is a map from
I looked at the sheet and I was like, maybe I should include that. I just realized that I probably should include that. Would all these questions combine into one whole proof, or would each question be its own proof?
All question will be its own proof.
Okay.
So first question is basically like property of image and pre-image. So one thing we have to make. Okay, so there's a few things. I mean, I will just give you some advice about proofwriting in general. First of all, you have to make sure that you understand all the symbol in the statement. Okay, so is inclusion okay?
Okay.
So you know what it means to be inclusion?
Like basically like we're saying that x1 is basically like a subset within x2. So basically it's like a smaller set within set 2.
Yeah. And another way to saying that is that every element in x1 is also an element inside of x2.
Wait, just say that again?
So maybe I can just rewrite it on the bottom. So the fact that x1 is contained inside of x2, this is really the same thing. I mean, that would be even the definition. That for all x inside of x1, we have that x is inside of x2.
Okay. I'll probably rewrite that actually.
But the thing here is, which is maybe the hardest part, which I just want to be sure we understand, is here do you understand what f of x1 means?
So that means a function on x2. Then that would mean that there's an x. So that means like basically x is in x1, but since x is also an element of x2, then that means basically they share the same elements.
So that's for the inclusion.
Yeah.
So just to be sure, this guy on the right those are subsets of B, right? They're not elements of B. They're very subset. Okay. And okay, so I guess now you know all the terms, so that's good.
Yeah.
So now the question is, what the goal of what we have to show? And here the thing we want to show is this inclusion, right?
Yeah.
So usually it would be a good idea to write goal is to show that we have f of x1, which is contained inside of f of x2.
Okay.
And after that, now you can do the thing you were doing, so you were kind of unraveling the definition, right?
Yeah, I think it's because like I was looking at it and then I was thinking about how functions work, and then like I was trying to get my brain to actually see what is it that I was missing, and I think you kind of filled it in already.
Yeah, and usually it's okay to rewrite the definition like that.
Yeah.
But usually it's better to look at the goal and see what is the goal saying, right? So starting by rewriting the definition of the goal, right? So what it means, what is exactly the set f of x1? What is the f of x2? And then after that, see what you can do with it.
Okay.
But you were doing it. You were doing.
Yeah. Because like, once I wrote this definition, I feel as if like is it okay if I erase what you wrote here?
Yeah.
Okay. Because it feels as if it's like kind of self-explanatory at this point, because at this point, since x1 is a subset of set x2, which implies that basically all of x in x1 exists and is an x, which is an x of an element in x2, then that means they share the same elements within the functions. So in this case, so since x is an element in x1 and x is an element of x2, being in x1 and I know that one was a little bit wordy, but I was just trying to like formulate everything in my head.
Yeah.
I guess this would probably be considered scratch work, or would this formulate as a formal proof?
I mean, it would be somewhat decent, but there's like some problematic part. But I will guide you, okay?
Mm-hmm.
So I will write on the button how I would have write. So maybe I can write suggested proof.
Yeah. Because I feel like I could have just done like, what do you call it? Just do it more axiomatic instead of just writing a whole paragraph.
Yeah, so here's how I would try to show. So first of all, I mean, when we have an implication, I don't usually rewrite the hypothesis. I mean, I will use it, but I will not rewrite it because it's kind of implied. So I will just focus on the conclusion.
Yeah.
So I want to show that f of x1 is inside of f of x2. Okay?
Mm-hmm.
So, I mean, if I want to be a little bit more pedantic, what I will say, okay, I have to show that every element does have to show that every y inside of f of x1 is also in, well, for every, okay, maybe I will just, I have to show, maybe I will write it more logically.
Mm-hmm.
For all y inside of f of x1, I have also that y is inside of f of x2. That's the definition of inclusion, right?
Uh-huh.
So that's my goal.
Okay.
So how do I prove that? So I have to prove it for every y, right?
Yeah.
So when you want to prove something with the quantifier for all, what you do is you just pick an element. So let y be an element of f of x1. Usually I like to think it as a challenge, right?
Uh-huh.
Like, come on, bro, give me some y inside of this, and I will show you that y is inside of that.
Mm-hmm.
You see, it's kind of the way I like to think about it.
Okay.
So let's y be inside of f of x1. So the fact that y is inside of f of x1 means that there exists x inside of x1
mm-hmm. such
that f of x is equal to y.
Okay.
Okay, my y is very bad right now, so we'll just rewrite it. Okay.
Yeah.
Hopefully you don't guys confuse it with a g. Okay. So I have this. So there exists an x inside of x1 shows that the f of x is equal to y, right?
Right.
But I know from the hypothesis that x1 is inside of x2, right?
Mm-hmm.
Thus, my little x will be also inside of x2, right?
Yeah.
Therefore, f of x will be by definition inside of the f of x2, right?
Is that supposed to be x1 or is it just f of x?
F of x.
Okay.
Yeah, it cannot be x, right? Because x live inside of the set A, right? And f of x live in B, so we have to.
You have to state this first. So basically, it's like the original function, but with just regular x. But since x is in both x1 and x2, basically you're just saying, okay, since x is an element of x1, and it's in f of x, but yet it's an element of x2, then that means it's like f of x1, you can now state that f of x1 is a subset of f of x2.
Yeah, so I'm not done yet, right?
Yeah.
So here I have his. If I want to clarify that, I would just say, well, what is the definition of this set? So we said that f of x2 is by definition, maybe I can put a little dot here, is by definition, or maybe I will use x prime just to avoid problems, is the image of some elements inside of x2, right? But here we just use the fact that x is inside of x2 to say that f of x has to be inside of f of x2, right?
Right.
But f of x is equal to y, right?
Right.
Original thing. Does this implies that y, which is equal to f of x, is contained inside. Okay, let's maybe write just y. Y is contained inside of f of x2. Thus, we've shown that for all y inside of f of x1, I have y which is inside of f of x2. In other words, we have shown that we have f of x1 which is inside of f of x2.
Okay. Yeah, I felt like it was more simplified than what I wrote.
Yeah, so here maybe if I go to your proof and I say what is maybe the part I found it a bit missing. So here's the problem here. First of all, you want to show something which is inside of B, right?
Yeah.
You want to show this inclusion, right?
Which inclusion?
I just go to my proof. I just circle the thing. I put a red square on it.
Yeah.
And what I did, I just unraveled this, and I say, okay, well, if we just unravel what it's meant to be inclusion, it's pretty much. I just end up having to show that, right? And what I would like you to do on your proof, is I would have liked you to do like I did here. I say, okay, let's pick y to be some element of f of x1. And using just the hypothesis and all the reasoning I just did, you want to figure out at the end that y is an element of f of x2.
Okay.
You see, in your proof, you kind of not did it, right?
Yeah, I basically based it on the definition of basically x1 is a subset of x2, and then work my way from there. Yeah. Yeah, you sort of avoid the question, right? A bit. I mean, at the end of the day, it's not very a big mistake in the sense like I see you understand why it's true, but I think it's some. I think for me, it's like with some proofs. I know you have to use the definition to basically prove that the idea that you're trying to prove, but like it's like you said, like some proofs you actually have to work backwards from what the conclusion is to actually show what it means to be true in that sense. So for yours, you prove that basically like, oh, we use f of x1 and is a subset of f of x2, and we just unravel that one to basically show why it's true. But I think for me, like whenever it comes to proofs, like I'm still on the whole, oh, if you're given like one idea, you use the definition of that said idea to prove this next idea that's there. Yeah. So I think that's the type of proof writing that I'm so used to. It's like just using the definitions to unravel the next thing that's supposed to be true. But I think for what you meant for this proof, like I think the majority of the proofs that you give in this assignment is mainly use the idea of what is given to you and try to unravel that to actually prove that it's true, right?
Yeah.
Okay, so we just gotta practice that more.
So basically, you have to have like a very eager eyes on the goal, right? So here you kind of, I mean, here this part is fine, right? You basically just say, okay, well, I will just rewrite the definition to make sure that I understand.
Yeah.
After that, you kind of play with it.
So go on.
But usually, what I would give as an advice is really like focus on the goal. Like the goal is the only thing that matters in the proof, right?
Okay.
You have to obtain the goal. So first of all, is the goal hard? Can you rewrite it in a way which is more simple? For example, here I have to show like this set is contained inside of this set, which is kind of it's kind of a big thing. There's like many elements inside of it.
Yeah.
So if I do like I did, I just say, well, what does it mean for this to be inside of it? I just say, well, I just have to show that if I pick an element inside of f of x1, it's also an element of f of x2.
So would you say that proofwriting, a majority of it is your method, basically just using the end result and kind of unraveling it to show that it's true, rather than more of what I was trying to do, just use the definitions to prove like this bigger idea exists based on your experience?
Well, I mean,
or it varies, like.
Yeah, I mean, usually you want to have a little bit of mixed step, right? You want some step to rewrite like the goal, right? And when you feel like the goal is like kind of manageable, come here, I just have to show that if I pick an arbitrary y inside of f(x1), I just have to show that it's
so you're basically saying is like look at the goal and basically ask, okay, can I use the goal? Can I use the end goal to basically find out if I have to prove that this is true, or do I have to use it to prove some bigger idea? Or something?
I mean, you cannot use the end goal, right? You cannot like assume the end goal. You have to deduce it. But I mean, at least you can like rewrite it. You can use equivalence to rewrite the end goal. You can use a sufficient condition to say, well, I mean, if I am able to show that, then it will imply the end goal or stuff like that.
Okay. And it looks like we have someone new in the chat. Ferris, Ferris, the best of the best. Nice to meet you, Ferris. Oh, you're 13 and you're in 8th grade. Shown a lot of math skills. I'm trying to enter the math community. Nice. Well, you're in the right place. You're in the right place, and thank you for the follow. Much appreciated. This is the right place and the right community to learn more math. I'm learning math as well, and I'm like 34, so you're way ahead of me in that regard. So, like, yeah, we're just learning a little bit of proofwriting right now, which is, I guess, like the real math, right, Sascha? Proofwriting is the real math. Yeah. No calculators, just writing variables. But yeah, thank you, Sascha, for like, as always, thank you for the lesson for the past 3 days.
So maybe I can just add the correction I wanted to add at the proof. So I would just say,
yeah, sure.
So maybe the sentence is missing is let's y be inside of f of x1. Then there exists some x inside of x1 such that we have y which is equal to f of x1, right?
Right.
And after that, I think your argument is sounded.
Wait, say that last part again.
I think the rest of your argument from that is sounded. So is logical. It's a good.
Yeah, I think I was just building on the logic, but I just didn't know how to write it correctly.
Yeah. So when you have inclusion, always remember to pick something inside of what you want to show the inclusion. So you pick something inside of y of x.
Okay.
Inside of f of x1.
Okay.
So if you add this little sentence, I think the rest is pretty decent.
Okay, I see. Because there are some math proofs that are just like mostly just explaining stuff, right? Because like I think like for me, I worry about writing the scratch work in the proof when it's not supposed to be there. And I still don't know the difference between writing scratch work and what's actually supposed to be in the proof. But I think we'll learn that like further down the line, right?
Yeah.
Okay.
But you're definitely improving a lot.
Oh, okay, thank you. I appreciate that. So, Sascha, what do you think we're gonna end up doing next week for the next 3 lectures?
So we're gonna build the rational.
Build the rationals, okay.
Yeah, which is like kind of a goal of us right now.
Okay.
And after that, we're gonna talk about sequences.
Sequences? Okay. Oh yeah, because that builds on real analysis, right?
Yeah, because basically, so okay.
Mm-hmm.
Okay, maybe I can write all the reals that are defined.
Yeah.
So, okay, first of all, we have to do like the introduction. We have to go from N, we have to go to Z, we have to go to Q.
Yeah.
And now we're at Q.
Okay.
And Q has like all the arithmetic property. You have division. You can do like a lot of stuff. And you have absolute value. I mean, we can define them before, but I mean they're used in Q. And what we would like to do is look at reasonable sequence. Okay. Okay, Peter.
Mm-hmm. Yeah.
And we want, like, for example, a sequence to be like decreasing.
Okay.
So an plus 1 is smaller than an, something like that, right?
Mm-hmm.
Like if you represent on the line, the points will go like something like an. Oh, sorry.
So basically what you wrote is like basically we're going to go into the rationals, and an is an element of the rationals, or in this case Q, and basically an plus 1 is less than or equal to an. Okay.
And assume like it's bounded by below by some constant. Okay.
Okay.
Some MEC. So what's gonna happen is over time you will get all your sequence like kind of getting very close to M, right?
Right.
And what would you expect is this sequence to converge, right?
Yeah.
Because there's like nothing wrong with this sequence. It's like decreasing, it's bounded by below. I mean, there's like no reason on earth why this sequence shouldn't converge, right?
Right.
Well, we're gonna see that one problem with the rational is actually there exists sequences that are decreasing and bounded by below, which are like very nice sequences, which do not converge.
Okay.
And that will tell us that the rational are missing points.
So Ferris is asking, how can an plus 1 be equal to n, an? That's a really good question. That's a really good question. Do you want to explain that?
Here I'm not saying that they're equal. I'm just saying it's decreasing. Like the term in the sequence are just getting smaller and smaller and smaller.
Yeah. So I'm guessing what's confusing you is when you see Ferris. I'm guessing you're confused because it says an plus 1. It's not like a multiplied by n plus 1. It's basically a. It has a subscript at the bottom. So basically like a with a little n at the bottom. So I'm guessing because I don't know if you covered that in your math class, but you're probably seeing it like this, which is not what Sascha's trying to write. It's actually just a with a little n like that. So hopefully that answers your question. It doesn't mean anything. It just means like another number in the sequence. It's like same as basically saying 2 is less than that doesn't make sense, but at the same time it's like setting it up like that. It's just another number within the number line.
Yeah. So I wrote, for example, an example. If you want to be more concrete, a of n is equal to 1 over n.
Yeah. There we go.
So that's an example of a sequence which is decreasing and bounded by below. It's bounded by 0.
Yeah.
In that case. And clearly this sequence converges to 0. There is like not very a doubt.
Mm-hmm.
But you will see that, those are supposed to be like the nicest function. In calculus, usually if you have a sequence which is bounded by below and decreasing, there is like no problems. You see it converge to something. But over the rational, that's not the case.
Okay.
And this will lead us to the problem that we cannot, for example, define continuity. We cannot we cannot define like a very good definition of continuity, limit and stuff like that. So they're missing point inside of Q. We have to add some points.
Right.
And that would be like the construction of the real numbers.
So basically it will be like the rational numbers, and then we're going to go into sequences, and thus we're being able to enter into the real numbers, right?
So yeah, so from Q, after that we will talk about sequences.
Yeah.
So we're gonna talk about convergent sequences.
Okay.
And a bit in the same fashion we did today. So you saw today we were, I mean, for example, in the integers we were not, in the natural number we were not able to talk about negative number, right?
Right.
And we kind of did like a little bit of a workaround, right, to be able to talk about negative number, right?
Right.
So for example, if you look at the equivalence relationship thing, well, we said our equivalence relationship is really a minus b1 should be equal to a2 minus b2, right?
Right.
But we play around to with this equation to not have to introduce negative numbers. So we say, well, this is the same thing as this, right?
Mm-hmm.
So we're gonna talk about a clever way to talk about the sequence, to tell the sequence in some sense that the sequence converge, but without having to tell about on what it converge.
Okay.
This is called Cauchy sequence.
I think I've seen that in books.
Yeah, and the moral is that Cauchy sequence should be sequence that converge. Like if you have a Cauchy sequence which is not convergent, it just means that your space is missing points.
Okay.
And basically what we're gonna do is we're just gonna take the Cauchy sequence, the set of Cauchy sequence, and quotient out by the some equivalence relationship.
Yeah.
And this will yield us the real numbers.
Okay.
And from now we will be able to start analysis properly.
Yep, and that's a sneak peek for what's going to come up for the next couple weeks, guys. So hopefully you're ready for a ride. We're going to be in for a ride. But we constructed the negative number, the negative numbers within the integers today. So once again, Sascha, thank you for the awesome lecture and the awesome knowledge, and also allowing us to practice what we learned a little bit today. Mm-hmm. So anything you would like to say to our audience before we depart for today?
Like and subscribe to Matt Spellbook, YouTube and Twitch.
And for all those that are in the chat, all my social medias are already just automatically in the chat right now. So you can basically join us on Discord. You can also join us on YouTube. Like, you know, if you basically had to pop in for the stream for a little while but you weren't able to catch up with the rest of it, you know, you can watch the rest of the stream there. But like I said, if my internet connection breaks off too many times during the stream, I'm actually recording each lecture, so I will upload those in case like the stream like basically becomes too fragmented. So thank you for joining us, guys. I think let's see if we can do a raid today. Let's see if there's any of our math friends available for today. Oh, Don is streaming today. We could probably give him a raid. And for anyone that basically is new to the channel, if you like math or physics, you know, drop a follow if you like, you know, learn with us. So we will do the raid command. So you guys can copy and paste that if you like. We'll copy that. And also, if you guys want to follow my gaming channel, you can follow my Uncle Talks channel, which is where I play video games. I will be streaming on that channel tonight, so if you would like to join us there, you're more than happy to do so. And if you're watching this on YouTube, all the links are in the description down below. Okay, we will raid into Don Does Math's channel. And Sascha, to finish everything off, I will basically bid you adieu. And hopefully you have a good rest of your day.
Yeah, you too, man.
Alright, take care, man.
See ya.
See you. Alright, guys, we will commence the raid into Don's channel. And always remember, everyone is precious. You guys are just as precious as everyone else. And we will see you guys next week. So take care, guys. Bye-bye.